Hello, and welcome to the Cosmic Sleep Lab. You can let yourself settle now. Whatever brought you here tonight, whatever thoughts you've been carrying, you can let them rest for a while. There's nothing you need to solve right now, nothing you need to remember or hold on to. This is a place where you can simply be still. The universe has been unfolding for billions of years without needing your attention. And tonight, it will continue to unfold, slowly and quietly, while you rest. You don't need to stay awake for any of this. You don't need to follow every word or remember every detail. This isn't a test. There's no quiz at the end. You're welcome to drift in and out, to let your mind wander, to fall asleep whenever your body is ready. Everything here will still be true tomorrow. The stars will still be burning, the galaxies will still be turning, and the mysteries we explore tonight will still be waiting, patient and unchanging, long after you wake. So take a breath, let your shoulders drop, let the weight of the day begin to drain away. We're going to move slowly through some of the quietest mysteries the universe holds. Not the loud ones, not the explosive or dramatic ones, just the slow, steady, gentle puzzles that have been unfolding across time and space since long before we were here to notice them. You're safe, you're still, and you can rest now. Let's begin. The universe is mostly empty. This is one of the first quiet mysteries. When we look out into space, what we see is not crowded or chaotic. It is vast and calm and almost entirely made of nothing. Between the stars, there is space. Between the galaxies, even more space. And in that space, there is mostly just darkness and distance, and the faint hum of radiation left over from the beginning of everything. If you could stand in the middle of intergalactic space, far from any galaxy, far from any star, you would see almost nothing. A few faint smudges of light in every direction, but mostly just black. Deep, quiet, endless black. And yet, even in that emptiness, there is something. There is a faint glow, a whisper of light. It comes from every direction at once, and it has been traveling through space for more than 13 billion years. We call it the cosmic microwave background. It is the afterglow of the Big Bang, the leftover heat from the moment the universe began, and it fills all of space, evenly, quietly, like a memory that never fades. When the universe was very young, it was hot. So hot that atoms could not form. So hot that light could not travel freely. Everything was a dense fog of energy and particles, glowing white hot, packed together in a space smaller than we can imagine. But then the universe expanded. It cooled. And after about 380,000 years, it cooled enough for atoms to form, for light to finally break free. That light has been traveling ever since. It has stretched and cooled as the universe expanded. What was once visible light, bright and blazing, is now microwave radiation, invisible to our eyes, but detectable by our instruments. And it is everywhere. No matter where you point a telescope, no matter where you look in the sky, you will find it. The same faint glow, the same ancient light. It is the oldest thing we can see, the earliest snapshot of the universe. And it tells us that the cosmos was once much smaller, much hotter, and much more uniform than it is today. But it also raises a mystery. The cosmic microwave background is almost perfectly smooth, almost perfectly uniform. The temperature is the same in every direction, to within a fraction of a degree. And that shouldn't be possible, because the universe is very large, so large that light from one side of the observable universe has not had time to reach the other side. So, how did both sides end up at the same temperature? How did distant regions of space, regions that could never have communicated with each other, end up so perfectly balanced? This is called the horizon problem. And the answer, scientists believe, lies in something that happened in the first fraction of a second after the Big Bang. Something called inflation. Inflation is the idea that the universe, in its earliest moments, expanded faster than the speed of light, much faster. In less than a trillionth of a second, the universe grew from something smaller than an atom to something larger than a galaxy. This rapid expansion smoothed out any irregularities. It stretched space itself so quickly that everything became uniform. And then, just as suddenly, inflation stopped. The universe continued to expand, but at a slower, steadier pace. And the evidence for this is written in the cosmic microwave background, because even though the background is smooth, it is not perfectly smooth. There are tiny fluctuations, tiny variations in temperature, regions that are slightly warmer or slightly cooler than average. These fluctuations are the seeds of everything that came later, the seeds of galaxies, the seeds of stars, the seeds of planets and moons, and eventually life. Gravity pulled matter toward the denser regions. Over millions of years, those regions grew. They collapsed. They formed the first stars, the first galaxies, the cosmic web of structure we see today. But the pattern of those fluctuations, the way they are distributed across the sky, matches exactly what inflation predicts. It is one of the most elegant confirmations in all of cosmology. A theory about the first instant of time, confirmed by light that has traveled for more than 13 billion years. And yet, we still do not know what caused inflation. We do not know what force or field or phenomenon could make space expand so fast. We do not know why it started. We do not know why it stopped. Inflation solves the horizon problem, but it also opens new mysteries. And that is how science works. Each answer leads to deeper questions. Each solution reveals new puzzles. The universe does not give up its secrets easily, but it does give them up slowly, quietly, one discovery at a time. Another mystery, quieter still, concerns the nature of time itself. We experience time as a flow, a river moving in one direction, past to present to future, always forward, never back. But the laws of physics do not require this. Most of the equations that describe the universe work just as well if time runs backward. If you filmed a planet orbiting a star and played the footage in reverse, the motion would still obey the laws of gravity. If you filmed particles colliding and reversed the tape, the physics would still hold. And yet, we never see time run backward. We never see a broken glass reassemble itself. We never see heat flow from a cold object to a hot one. We never see the past change. This is called the arrow of time, and it is one of the deepest mysteries in physics. The arrow of time is not a law. It is a tendency, a statistical inevitability. It arises not from the fundamental rules of the universe, but from the way those rules play out over large numbers of particles. It is connected to a concept called entropy. Entropy is a measure of disorder, of randomness, of the number of ways a system can be arranged. A broken glass has high entropy. There are many ways the pieces can be scattered. A whole glass has low entropy. There is only one way for it to be intact. The second law of thermodynamics says that entropy always increases. Systems move from order to disorder, from low entropy to high entropy, never the reverse. And this is why time has an arrow. When you break a glass, you are increasing entropy. The pieces scatter, the energy spreads out, and the universe moves toward a more disordered state. To reassemble the glass, you would need to decrease entropy. You would need to gather all the pieces, all the energy, all the vibrations, and put them back exactly as they were. This is not impossible. It does not violate any fundamental law, but it is extraordinarily unlikely. So unlikely that it will never happen by chance. And so, time flows forward, because entropy increases, because disorder grows, because the universe is moving from a state of low entropy to a state of high entropy. But this raises another mystery. If entropy always increases, then the universe must have started in a state of very low entropy, a state of very high order, and we do not know why. Why was the early universe so orderly? Why was everything so smooth, so uniform, so finely arranged? This is called the past hypothesis, the assumption that the universe began in a low entropy state. And it is one of the most important assumptions in all of physics. Without it, the second law of thermodynamics would not work. Without it, time would have no arrow. Without it, the universe would make no sense. And yet, we do not know why it is true. We do not know what set the initial conditions. We do not know why the Big Bang began with such low entropy. Some scientists believe the answer lies in quantum mechanics. Others believe it lies in the nature of gravity. Still others believe it is simply a brute fact, a boundary condition that requires no explanation. But the mystery remains. Time flows forward. Entropy increases. The universe grows more disordered with every passing moment. And we do not know why it started any other way. There is a place in space where time behaves even more strangely. Near a black hole, time slows down. Not for the person falling in. For them, time feels normal. But for someone watching from far away, time near the black hole appears to stretch, to crawl, to nearly stop. This is called time dilation, and it is a consequence of Einstein's theory of general relativity. General relativity tells us that gravity is not a force. It is a curvature of space-time. Massive objects bend the fabric of space and time around them, and the stronger the gravity, the more extreme the curvature. Near a black hole, gravity is so strong that space-time is bent almost to breaking, and time, as a result, slows down. If you could watch someone fall toward a black hole, you would see them slow down as they approached the event horizon. Their movements would become sluggish. Their clock would tick more and more slowly. And at the event horizon itself, they would appear to freeze. But, from their perspective, nothing unusual would happen. They would fall through the event horizon in a finite amount of time. They would continue falling toward the singularity at the center, and they would never see themselves freeze. This is one of the strangest features of black holes. The event horizon is not a physical barrier. It is simply the point of no return, the boundary beyond which nothing, not even light, can escape. And yet, from the outside, it looks like time itself has stopped there. This leads to a paradox. If you watch someone fall into a black hole, you will never see them cross the event horizon. You will see them slow down, redden, and fade, but never quite as disappear. And yet, from their perspective, they do cross. They do fall in. They do reach the singularity. So what is the truth? Do they cross or not? The answer, according to general relativity, is both. It depends on your perspective. It depends on where you are and how you measure time. This is the nature of space-time. It is not absolute. It is not the same for everyone. It is relative, flexible, dependent on motion and gravity and the path you take through the universe. And near a black hole, this relativity becomes extreme. Time is not a river, it is a dimension, a part of the fabric of reality. And like space, it can be stretched, compressed, and curved. Black holes are the places where this curvature is most severe, where time and space become so warped that our intuitions break down, where the rules of everyday experience no longer apply. And yet, black holes are not rare. There are millions of them in our galaxy alone, perhaps billions. They are a natural consequence of stellar evolution, the final stage in the life of the most massive stars. When a star runs out of fuel, it can no longer support itself against gravity. It collapses. And if it is massive enough, it collapses all the way down to a point, a singularity, a place where density becomes infinite, and the laws of physics, as we know them, cease to function. Around that singularity, space-time is so curved that nothing can escape, and the event horizon forms. From the outside, a black hole is invisible. It emits no light. It reflects no light. It is a hole in space, a region of absolute darkness. But we can detect black holes by their effects, by the way they bend light, by the way they pull on nearby stars, by the way they heat up gas as it spirals inward, glowing brightly just before it disappears forever. And we have even taken a picture of one. In 2019, the Event Horizon Telescope captured an image of the black hole at the center of the galaxy M87. It showed a dark circle surrounded by a glowing ring of light, the shadow of the event horizon, the boundary of no return. It was the first direct image of a black hole, and it confirmed what general relativity had predicted more than a century earlier. Black holes are real. They exist, and they are exactly as strange as the equations said they would be. But they are also quiet, patient, waiting in the darkness, slowly consuming anything that comes too close. They do not explode. They do not shout. They simply exist, warping space-time, bending light, slowing time. And they will be here long after the stars have burned out, long after the galaxies have faded, long after the universe has grown cold and dark, because black holes evaporate very, very slowly. this evaporation is another mystery, another quiet puzzle. Stephen Hawking discovered that black holes are not entirely black. They emit radiation, a faint glow of particles that leak out from the event horizon. This radiation is called Hawking radiation, and it arises from the quantum nature of empty space. Empty space is not truly empty. It is filled with virtual particles, pairs of particles and antiparticles that pop into existence and annihilate each other almost instantly. Normally, these virtual particles have no lasting effect. They appear and disappear too quickly to notice. But near the event horizon of a black hole, something different happens. One particle of the pair can fall into the black hole, while the other escapes. The escaping particle becomes real. It carries energy away from the black hole. And because energy is conserved, the black hole loses mass. Over time, very slowly, the black hole evaporates. For a large black hole, this process takes an unimaginably long time, longer than the current age of the universe, longer than the lifetime of the stars. But for a small black hole, the process is faster. And in the far, far future, when all the stars have died and the universe is cold and dark, black holes will be the last sources of energy, the last points of light. And then, one by one, they too will fade. This evaporation leads to a paradox, a mystery that has puzzled physicists for decades. When a black hole evaporates, what happens to the information that fell into it? In quantum mechanics, information cannot be destroyed. It can be scrambled, hidden, or transformed, but it must always be preserved. But if a black hole evaporates completely, where does the information go? Does it escape in the Hawking radiation? Does it remain inside, somehow encoded in the final burst of energy? Or is it lost forever? This is called the black hole information paradox, and it is one of the deepest unsolved problems in theoretical physics. Some scientists believe the information is preserved, that it is encoded in the radiation in a way we do not yet understand. Others believe the paradox reveals a flaw in our understanding of quantum mechanics or general relativity. Still others believe the answer lies in a theory we have not yet discovered, a theory that unites quantum mechanics and gravity, a theory of everything. But for now, the paradox remains. Black holes keep their secrets. They swallow information. They warp time. They bend light. And they do it all in silence. Silence is another feature of space. Sound cannot travel in a vacuum. There is no air to carry the vibrations, no medium for the waves to move through. And so, space is quiet. Perfectly, utterly quiet. The explosions of supernovae, the collisions of galaxies, the roar of gas falling into black holes, all of it happens in silence. We see the light. We detect the radiation, but we hear nothing. This silence is part of what makes space so peaceful, so calming. There is no noise, no distraction, just light and darkness and the slow dance of gravity. But there is one exception: gravitational waves. Gravitational waves are ripples in space-time itself. They are created when massive objects accelerate, when black holes collide, when neutron stars spiral together, when the fabric of space is shaken by violent events. These ripples travel at the speed of light, spreading outward in all directions, and as they pass through space, They stretch and compress everything in their path, including us. When a gravitational wave passes through Earth, it changes the distance between objects, very slightly, by less than the width of an atom, but enough to detect. And we have detected them. In 2015, the LIGO Observatory recorded the first direct detection of gravitational waves. They came from two black holes, more than 1 billion light-years away, that had spiraled together and merged. The signal lasted less than a second, a faint chirp, a rising tone, and then silence. But in that chirp was a wealth of information. The masses of the black holes, the distance to the collision, the shape of space-time as it rippled and settled. It was the first time we had heard the universe, not with light, not with particles, but with gravity itself. Since then, dozens more gravitational waves have been detected, from black holes, from neutron stars, from events we are still working to understand. And each one is a voice, a signal, a message from the distant universe, carried not by light, but by the fabric of space and time. Gravitational waves are silent in the traditional sense. They do not vibrate air. They do not make sound. But they do vibrate space-time. And when we convert their signal into audio, they make a sound, a chirp, a whistle, a hum. It is the sound of the universe itself, singing. And it is one of the most profound discoveries in modern science, because it opens a new way of observing the cosmos, a way that does not rely on light, a way that can see through dust and gas and darkness, a way that lets us listen to the universe, not just look at it. And what we are hearing is beautiful, quiet, steady, the slow collision of massive objects, the merger of black holes, the spin of neutron stars, all of it happening in the deep, dark silence of space, all of it sending ripples through the fabric of reality, ripples that travel for billions of years, that cross unimaginable distances, that arrive here, faint and fading, just strong enough for us to detect. And in those ripples, we find answers and more mysteries, because the universe is full of both. One of the quietest mysteries involves something we cannot see at all: dark matter. Most of the matter in the universe is invisible. It does not emit light. It does not absorb light. It does not reflect light. It passes through ordinary matter as if it were not there. And yet, we know it exists. We know because of the way galaxies move, the way they spin, the way they hold together. When astronomers measure the speed of stars orbiting the center of a galaxy, they find something strange. The stars at the edge of the galaxy are moving too fast, much too fast. According to the laws of gravity, those stars should be moving slower, or they should fly off into space. The visible matter in the galaxy, the stars and gas and dust, does not produce enough gravity to hold them in place. And yet, they stay. They orbit. They remain bound to the galaxy. The only explanation is that there is more matter there, matter we cannot see, matter that provides the extra gravity needed to keep the galaxy together. This invisible matter is called dark matter, and it makes up about 85% of all the matter in the universe. We do not know what it is made of. We do not know what particles compose it. We have never detected it directly, but we see its effects everywhere. in the rotation of galaxies, in the motion of galaxy clusters, in the bending of light around massive objects, in the structure of the cosmic web. Dark matter is woven through the universe. It forms a scaffolding, a framework, upon which galaxies form. It pulls ordinary matter together. It shapes the large-scale structure of the cosmos. Without dark matter, galaxies would not exist. Stars would not exist. We would not exist. And yet, we do not know what it is. Scientists have proposed many candidates. Exotic particles with names like WIMPs and actions, primordial black holes, modified theories of gravity. But so far, none of these ideas have been confirmed. Experiments deep underground search for dark matter particles. Detectors in space look for signs of dark matter annihilation. Particle accelerators try to create dark matter in the lab, but the universe keeps it secret. Dark matter remains invisible, silent, undetected. It does not interact with light. It does not interact with ordinary matter, except through gravity. It is a ghost, a shadow, a presence we can infer but never touch. And it is everywhere. Right now, dark matter is passing through you. Billions of particles streaming through your body, through the earth, through everything, without leaving a trace. You cannot feel it, you cannot see it, but it is there, and it has been there since the beginning. Dark matter was present in the early universe. It clumped together under gravity. It formed the first structures. It pulled hydrogen gas into the first galaxies. It is older than the stars, older than the planets, older than anything we can see. And it will be here long after everything else has faded, because dark matter does not decay. It does not burn out. It does not evaporate. It simply exists, patient, invisible, eternal. There is another invisible component to the universe, something even stranger than dark matter: dark energy. Dark energy is the name we give to the force that is causing the universe to expand faster and faster. For most of the history of the universe, the expansion was slowing down. Gravity was pulling everything together, trying to halt the expansion, perhaps even reverse it. But about 5 billion years ago, something changed. The expansion began to accelerate. Galaxies began to move away from each other more quickly. The space between them began to grow at an increasing rate. And this acceleration has continued ever since. Scientists discovered this in the late 1990s by studying distant supernovae. These exploding stars are so bright that they can be seen across billions of light years, and they have a predictable brightness, which makes them useful as distance markers. When astronomers measured the distance to these supernovae and compared it to their redshift, the amount their light had been stretched by the expansion of the universe, they found something unexpected. The distant supernovae were farther away than they should have been. The universe had expanded more than expected. The only explanation was that the expansion was accelerating, that some unknown force was pushing space apart. This force is called dark energy, and it makes up about 68% of the total energy in the universe. We do not know what it is. We do not know where it comes from. We do not know why it exists. It could be a property of space itself, a kind of energy that is built into the fabric of the vacuum. Einstein called it the cosmological constant. Or it could be a new kind of field, a dynamic energy that changes over time. Scientists call this quintessence. Or it could be a sign that our understanding of gravity is incomplete, that general relativity needs to be modified on the largest scales. But we do not know. What we do know is that dark energy is causing the universe to expand faster and faster, and this has profound consequences for the future. As the universe expands, galaxies move farther apart. The space between them grows, and eventually, distant galaxies will be moving away from us faster than the speed of light. Not because they are moving through space, but because space itself is expanding. And when that happens, their light will never reach us. They will disappear beyond the cosmic horizon. They will be lost to us forever. In the far future, billions of years from now, the only galaxies we will be able to see are the ones in our local group: the Milky Way, Andromeda, and a few dozen smaller galaxies, all bound together by gravity. Everything else will have vanished. The universe will appear empty, dark, quiet, and eventually, even those nearby galaxies will merge. They will collide and combine into a single, giant, elliptical galaxy. And then, there will be nothing else to see. No other galaxies, no other stars beyond our own. The universe will still be expanding. Dark energy will still be pushing space apart. But we will be alone. This is called the Big Chill, or the heat death of the universe. It is the ultimate fate of a universe dominated by dark energy. A future where everything grows cold and dark and still. The stars will burn out. One by one, they will exhaust their fuel and fade. The smallest stars, the red dwarfs, will last the longest, trillions of years. But eventually, even they will die. And when the last star goes out, the universe will be dark. There will be no more light, no more heat, no more energy flowing from one place to another. Only black holes will remain, and even they will evaporate slowly over timescales so long that the current age of the universe is less than a blink. And then there will be nothing, just empty space, cold, dark, expanding forever. This is the fate predicted by our current understanding of dark energy. A quiet end, a slow fade, a universe that does not end in fire but in silence. But we do not know if this is truly what will happen, because we do not understand dark energy. We do not know if it is constant. We do not know if it will change. Perhaps dark energy will grow stronger. Perhaps it will tear apart galaxies, stars, planets, atoms. Perhaps it will end the universe in a big rip. Or perhaps dark energy will weaken. Perhaps the expansion will slow again. Perhaps gravity will eventually win, and the universe will collapse back in on itself, ending in a big crunch. Or perhaps something else will happen. Something we have not imagined. Something that depends on physics we have not yet discovered. The future is uncertain. The universe keeps its secrets. But for now, the expansion continues. Dark energy pushes. Space grows. And we drift slowly toward a future we cannot see. There is a question that arises naturally from all of this. Why does the universe have the properties it does? Why is the cosmological constant the value it is? Why is dark energy so weak? If dark energy were slightly stronger, the universe would have expanded too quickly for galaxies to form. If it were slightly weaker, the universe might have collapsed long ago. If the laws of physics were slightly different, stars might not ignite, atoms might not form, life might never arise. The universe seems finely tuned, balanced on a knife edge, perfectly calibrated to allow complexity, structure, and life. This is called the fine-tuning problem, and it is one of the most profound mysteries in cosmology. Some scientists believe the answer is the anthropic principle, the idea that the universe must have the properties it does, because if it did not, we would not be here to observe it. In other words, we exist because the universe allows us to exist, and if the universe were different, we would not be asking the question. This is not a satisfying answer to everyone. It feels circular. It does not explain why the universe is the way it is, only why we are able to observe it. Others believe the answer lies in the multiverse, the idea that our universe is just one of many, that there are countless other universes, each with different laws of physics, different constants, different properties. In most of those universes, conditions are not right for life. Stars do not form. Galaxies do not form. Complexity does not arise. But in a few universes, by chance, the conditions are just right. And in those universes, life can emerge. Observers can exist. We live in one of those rare universes, not because it was designed for us, but because we could only exist in a universe like this. The multiverse is a controversial idea. It is difficult to test, difficult to prove or disprove. Some scientists embrace it. Others reject it as unscientific. But it is one possible answer to the fine-tuning problem. One way to explain why the universe has the properties it does. Another possibility is that we simply do not understand the laws of physics well enough, that there is a deeper theory, a more fundamental explanation, that will show why the constants have the values they do. Perhaps string theory will provide that answer. Perhaps loop quantum gravity. Perhaps something else entirely. But for now, the mystery remains. The universe is finely tuned, and we do not know why. There is a related mystery about the number of dimensions. We experience 3 dimensions of space: length, width, height, and 1 dimension of time. But some theories of physics suggest there may be more dimensions. Dimensions we cannot perceive. Dimensions that are curled up, hidden, too small to detect. String theory, for example, requires 10 dimensions, or 11 in some versions. In string theory, the fundamental building blocks of the universe are not particles, but tiny, vibrating strings. These strings exist in a space with more than 3 dimensions, and the way they vibrate determines what kind of particle they appear to be. An electron is a string vibrating one way. A quark is a string vibrating another way. A photon is a string vibrating yet another way. The extra dimensions are compactified, curled up into shapes so small that we cannot see them, smaller than atoms, smaller than protons, smaller than anything we can measure. But they are there, and they affect the way the strings vibrate. They affect the properties of particles. They affect the laws of physics. If string theory is correct, then the universe is much stranger than it appears. Space is not 3-dimensional. It is 10-dimensional, or 11. and most of those dimensions are hidden from us. But string theory is not proven. It is a mathematical framework, a set of equations. It makes predictions, but many of those predictions are difficult or impossible to test with current technology. And so the question remains, are there extra dimensions? And if so, why are they hidden? One possibility is that the extra dimensions are small because of the way the universe evolved. Perhaps they started out the same size as the other dimensions, but something caused them to curl up, to compactify. Another possibility is that the extra dimensions are not small at all, that they are large, but we are confined to a three-dimensional surface within them, like a sheet of paper in a three-dimensional room. We can move along the paper, but not off it. This is called the brain world scenario. The idea that our universe is a three-dimensional brain embedded in a higher dimensional space. If this is true, then gravity might be able to leak into the extra dimensions. And this could explain why gravity is so much weaker than the other forces. Electromagnetism, the strong force, and the weak force are all confined to our brain, but gravity spreads out into the higher dimensions, and so it appears weaker to us. This is a speculative idea. There is no direct evidence for it, but it is consistent with the mathematics of string theory, and it offers a possible explanation for one of the puzzles of particle physics. The question of extra dimensions is still open. We do not know if they exist. We do not know how many there are. We do not know why they would be hidden. But the possibility is tantalizing. The idea that the universe has more structure, more complexity, more depth than we can perceive. That reality extends beyond what we can see, beyond what we can measure, beyond what we can imagine, and that somewhere in those hidden dimensions there are truths we have not yet discovered. Another quiet mystery involves the nature of quantum mechanics itself. Quantum mechanics is the theory that describes the behavior of particles at the smallest scales, and it is one of the most successful theories in all of science. It has been tested countless times. It has made predictions that have been confirmed to extraordinary precision. It underlies all of modern technology. Computers, lasers, smartphones, medical imaging, all of it depends on quantum mechanics. And yet, we do not fully understand what it means. At the heart of quantum mechanics is the idea of superposition, the idea that a particle can exist in multiple states at once. It can be in two places at the same time. It can spin in two directions at the same time. It can be both a wave and a particle. But when we measure the particle, when we observe it, the superposition collapses. The particle chooses one state, one position, one spin, and we do not know why. This is called the measurement problem, and it is one of the deepest puzzles in quantum mechanics. What counts as a measurement? What causes the collapse? Is it the act of observation, the interaction with a detector, the involvement of consciousness? No one knows. There are many interpretations of quantum mechanics, many ways of thinking about what is happening. The Copenhagen interpretation says that the wave function, the mathematical description of the superposition, is not real. It is just a tool for calculating probabilities. The collapse happens when we measure, but there is no deeper reality behind it. The many worlds interpretation says that the wave function never collapses. Instead, every possible outcome happens. The universe splits into multiple branches. In one branch, the particle is here. In another branch, it is there. And both branches are equally real. The pilot wave interpretation says that particles do have definite positions, even when we are not measuring them. They are guided by a wave, a field that fills all of space. The wave is real. The particle is real. And there is no collapse. Each interpretation gives the same predictions. Each one matches the experiments. But they paint very different pictures of reality, and we do not know which one is correct, or if any of them are correct. Quantum mechanics works. It predicts, it explains, but it does not tell us what is really happening. It does not tell us what reality is like when no one is looking. And this is deeply unsettling, because it suggests that the universe is fundamentally strange, that reality is not what it seems, that the act of observation plays a role in shaping what exists, or perhaps it suggests that our language, our concepts, our intuitions are simply inadequate, that the quantum world does not fit into the categories we use to describe the everyday world. Particles are not tiny billiard balls. Waves are not ripples in water. Superposition is not a particle being in two places at once. These are just metaphors, approximations, ways of translating the mathematics into words. But the mathematics is what is real. The equations are what describe the universe, and they do not care about our intuitions. Quantum mechanics is a mystery we live with, a theory we use every day without fully understanding what it means. And perhaps that is enough. Perhaps the universe does not owe us an explanation. Perhaps reality is simply what the equations say it is: strange, counterintuitive, impossible to visualize, but real nonetheless. One of the strangest predictions of quantum mechanics involves something called entanglement. Entanglement is a connection between particles, a correlation that persists even when the particles are separated by vast distances. If two particles are entangled, measuring one of them instantly affects the other, no matter how far apart they are. This does not mean information is traveling faster than light. It does not mean there is a signal passing between them. The connection is more subtle than that. But it is real. It has been tested. It has been confirmed. Einstein called it spooky action at a distance. He did not like it. He thought it suggested that quantum mechanics was incomplete, that there must be some hidden variables, some deeper reality that explained the correlation. But experiments have shown that Einstein was wrong. There are no hidden variables. The entanglement is fundamental. It is built into the fabric of quantum mechanics, and it is one of the most profound features of the universe. Entanglement means that particles are not independent. They are connected. They are part of a larger whole. Even when separated by light years, they remain linked. They share a quantum state. They are, in some sense, one system. This has deep implications for the nature of reality. It suggests that the universe is not made of separate, isolated objects. It is a web of connections, a network of relationships. Particles do not have properties on their own. They have properties in relation to other particles, in relation to the whole. This is a shift in perspective, a move away from the idea of a universe made of independent parts toward the idea of a universe that is fundamentally interconnected. And It is not just a philosophical idea. It is a physical fact, confirmed by experiment, used in technology. Quantum computers rely on entanglement. Quantum cryptography relies on entanglement. Future technologies will rely on it even more. But we still do not fully understand it. We do not know why entanglement exists. We do not know what it means for the nature of space and time. Some physicists believe that entanglement is more fundamental than space, that space itself emerges from the pattern of entanglement between particles. This is a radical idea. It suggests that space is not a container, not a stage on which events unfold. It is a consequence, a byproduct, an emergent property of quantum connections. If this is true, then the universe is even stranger than we thought. Space is not fundamental. Distance is not fundamental. Only the web of entanglement is real, and everything else is built on top of that. This is still speculative, still theoretical, but it is a direction that research is moving, a possibility that physicists are exploring, and it is one more mystery, one more quiet puzzle, one more hint that the universe is deeper, richer, more interconnected than we ever imagined. There is a type of particle that passes through everything. Right now, trillions of them are passing through your body, through the walls, through the earth, through everything solid, as if it were not there at all. They are called neutrinos. Neutrinos are among the most abundant particles in the universe. They are produced in the cores of stars, in supernovae, in the Big Bang itself. They stream out from the sun in vast numbers, flooding through space, through planets, through us, and they barely interact with anything. A neutrino could pass through a light year of solid lead and not hit a single atom. They are ghostly, insubstantial, almost impossible to detect. And yet, we have detected them, deep underground, in massive tanks of water. Scientists have built detectors. They wait. They watch. And occasionally, very rarely, a neutrino will collide with a water molecule. It will produce a flash of light, a brief spark, and the detector will record it. These detections are precious. Each one tells us something about where the neutrino came from, what produced it, how long it has been traveling. Neutrinos from the sun tell us about the nuclear reactions happening in its core. Neutrinos from supernovae tell us about the deaths of massive stars. Neutrinos from the early universe carry information about the Big Bang itself. They are messengers, travelers from distant places and distant times. And because they interact so weakly, they can carry information that light cannot. Light can be absorbed, scattered, blocked by dust and gas. But neutrinos pass through everything. They arrive here unchanged, carrying their message intact. And that message is often surprising. In the 1960s, scientists built the first detector to measure neutrinos from the sun. They wanted to test their understanding of how stars work, to confirm that the sun was powered by nuclear fusion. But when they measured the number of neutrinos arriving from the sun, they found a problem. There were too few. Only about 1/3 of the expected number were arriving. The rest were missing. This became known as the solar neutrino problem, and it puzzled scientists for decades. Some thought the problem was with the detector. Perhaps it was not sensitive enough. Perhaps it was missing some neutrinos. Others thought the problem was with the theory. Perhaps the sun was not fusing hydrogen the way we thought. Perhaps our models were wrong. But the answer turned out to be stranger than either of those possibilities. The neutrinos were not missing. They were changing. Neutrinos come in three types, three flavors: electron neutrinos, muon neutrinos, and tau neutrinos. The Sun produces electron neutrinos. But as those neutrinos travel from the Sun to the Earth, they oscillate. They change from one flavor to another, and by the time they arrive here, only about 1/3 of them are still electron neutrinos. The detector was only sensitive to electron neutrinos, so it was only seeing 1/3 of the total. The rest had changed flavor and were passing through undetected. This discovery solved the solar neutrino problem, but it also revealed something profound about neutrinos themselves. For neutrinos to oscillate, they must have mass. This was unexpected. For many years, scientists thought neutrinos were massless. The equations of particle physics suggested they should be massless, like photons. But the oscillations proved otherwise. Neutrinos have mass, a very small mass, so small that it is difficult to measure. But it is there, and this has implications for the universe as a whole. If neutrinos have mass, then they contribute to the total mass of the universe, and because they are so abundant, even a tiny mass adds up. Scientists estimate there are about 330 neutrinos per cubic centimeter in the universe, left over from the Big Bang, cooled by the expansion of space, no longer hot and energetic, but still present, still moving, still everywhere. If each of those neutrinos has even a tiny mass, then together they account for a significant fraction of the matter in the universe. Not as much as dark matter, but more than all the visible stars and gas combined. Neutrinos are part of the cosmic inventory, part of the structure, part of the web of matter that shapes the universe. And yet, they are almost invisible, almost intangible, passing through everything, affecting almost nothing, but always there. They are quiet travelers, silent messengers, witnesses to events we can barely imagine. And they remind us that the universe is full of things we cannot see, cannot touch, cannot directly perceive. But they are real. They exist, and they matter. Another mystery involves something much larger than a particle. It involves the largest structures in the universe. Galaxies are not scattered randomly through space. They are arranged in patterns, in clusters, in filaments, in vast webs of structure that stretch across hundreds of millions of light years. These structures are called the cosmic web, and it is one of the most striking features of the universe. If you could step back far enough, if you could see the universe on the largest scales, you would see that galaxies are not evenly distributed. They form sheets and filaments, like the strands of a spider's web, and between those strands are enormous voids, regions of space that are nearly empty. The cosmic web formed over billions of years, shaped by gravity and dark matter. In the early universe, matter was distributed almost uniformly, almost smooth, but there were tiny fluctuations, tiny variations in density. Gravity pulled matter toward the denser regions. Over time, those regions grew. They attracted more matter. They became denser still, and the less dense regions became emptier. Matter flowed out of them toward the denser areas. Slowly, over hundreds of millions of years, the structure emerged. Filaments formed, clusters formed, voids formed, and the pattern that emerged was the cosmic web. It is a natural consequence of gravity, a structure that arises inevitably from the initial conditions of the universe. But it is also beautiful, delicate, complex. The filaments are like threads of light stretching across the darkness. The clusters are like knots where many threads come together, and the voids are like empty chambers, vast and silent. The cosmic web is held together by dark matter. The filaments are made mostly of dark matter, with galaxies and gas embedded within them. The dark matter provides the gravity, the scaffolding, the framework, and it is stable. The cosmic web does not collapse. It does not fall apart. It simply exists, slowly evolving as the universe expands. Galaxies move along the filaments. They flow toward the clusters. They merge. They interact. They are drawn together by gravity, guided by the structure of the web. And we are part of this structure. The Milky Way is part of a small cluster called the local group. The local group is part of a larger structure called the Virgo supercluster. And the Virgo supercluster is part of an even larger structure called Laniakea. Laniakea is a supercluster of superclusters, a vast region of space, 500 million light-years across, containing about 100,000 galaxies, and we are moving through it. The Milky Way is being pulled toward the center of Laniakea, toward a region called the Great Attractor. We are flowing along one of the filaments of the cosmic web, drawn by gravity, moving through space at hundreds of kilometers per second. This motion has been ongoing for billions of years, and it will continue for billions more. We are not stationary. We are not isolated. We are part of a flow, a current, a river of galaxies moving through the structure of the universe. And this flow is one of the quiet motions of the cosmos, slow, steady, inevitable. It is not something we can feel, not something we experience directly, but it is happening all the time, beneath everything else. The cosmic web is a reminder that the universe has structure on the largest scales, that even the voids, the empty spaces, are part of a pattern, that everything is connected. And it is also a reminder that we are small, that our galaxy is one of many, that the structures we are part of extend far beyond what we can see. But there is something comforting in that, something peaceful. We are part of something larger. We are woven into the fabric of the universe, and that fabric has been unfolding for billions of years and will continue to unfold for billions more. We do not need to understand all of it. We do not need to grasp the full scale. We simply need to know that we are part of it, and that is enough. One of the mysteries of the cosmic web involves the voids themselves. The voids are not completely empty. They contain some galaxies, some matter, but they are far less dense than the filaments and clusters, and they are very large. Some voids are hundreds of millions of light-years across, enormous bubbles of near emptiness, surrounded by walls of galaxies. Inside a void, space is quieter, calmer. There is less gravity pulling things together, less structure forming. Galaxies and voids are often isolated. They evolve more slowly. They have fewer interactions, fewer mergers, fewer disturbances. In some ways, a void is the most peaceful place in the universe, away from the crowded clusters, away from the constant gravitational tug and pull, just empty space, stretching in every direction. But the voids are also mysterious. We do not know exactly how they formed. We know that gravity shaped them, but the details are still being worked out. We do not know if they will always exist, or if they will eventually be filled in as the universe continues to evolve. We do not know if there is something special about the voids, if they play a role in the structure of the universe that we do not yet understand. But they are there, vast and empty and quiet, a natural part of the cosmic web. And they remind us that the universe is not uniform, that it has texture, that it has regions of density and regions of emptiness. And both are necessary. Both are part of the pattern. Another quiet mystery involves the motion of galaxies within clusters. When astronomers measure the speeds of galaxies in a cluster, they find something strange. The galaxies are moving too fast. According to the laws of gravity, based on the visible matter in the cluster, the galaxies should be moving slower, or they should escape. The cluster should fly apart. But it does not. The galaxies remain bound. They stay together. This was one of the first clues that dark matter exists, that there is more matter in the cluster than we can see. Invisible matter, providing the extra gravity needed to hold the cluster together. This observation was made in the 1930s by an astronomer named Fritz Zwicky. He studied the Coma cluster, a large cluster of galaxies, and measured the speeds of the galaxies within it. He found that they were moving much faster than expected, and he concluded that there must be missing mass, dark matter. At the time, his idea was not widely accepted. It seemed strange, unlikely. Why would there be invisible matter? But over the decades, more evidence accumulated. The rotation curves of galaxies, the bending of light around massive objects, the structure of the cosmic web, all of it pointed to the same conclusion. Dark matter exists, and it is everywhere. Galaxy clusters are some of the best places to study dark matter, because they contain so much of it, and because the effects are so clear. When light from a distant galaxy passes near a massive cluster, the light is bent by gravity. This is called gravitational lensing. The cluster acts like a lens, focusing and distorting the light. And by studying the amount of distortion, astronomers can map the distribution of mass in the cluster. What they find is that most of the mass is not in the galaxies. It is in the space between them, in the dark matter. The dark matter forms a halo around the cluster, a smooth, invisible cloud that extends far beyond the visible galaxies. And this halo provides the gravity, the structure, the glue that holds the cluster together. Without dark matter, clusters would not exist. Galaxies would not stay together. The cosmic web would not have formed. Dark matter is essential, fundamental, invisible but present, and it is one of the quiet forces shaping the universe. There is a question about the future of galaxies. What will happen to them in the far future as the universe continues to expand? The answer depends on dark energy, on whether the acceleration of the universe continues, on whether space keeps expanding faster and faster. If dark energy remains constant, then the future is clear. The universe will keep expanding. Galaxies will move farther apart, and eventually, they will be so far away that their light can no longer reach us. The only galaxies we will see are the ones in our local group: the Milky Way, Andromeda, and a few dozen smaller galaxies. And even those galaxies will merge. In about 4 billion years, the Milky Way and Andromeda will collide. They will pass through each other, their stars mingling, their gas clouds colliding and forming new stars. And then they will fall back together. They will merge into a single, large elliptical galaxy. This new galaxy will be the center of our local universe, the only structure we can see, the only light in the darkness. All other galaxies will have vanished beyond the cosmic horizon. The universe will appear empty, silent, still. And then, over trillions of years, the stars in that galaxy will burn out. One by one, they will exhaust their fuel and fade. The smallest stars, the red dwarfs, will last the longest, tens of trillions of years, but eventually even they will die. And when the last star goes out, the universe will be dark. No more light, no more heat, just cold, dead remnants, white dwarfs, neutron stars, black holes, and empty space expanding forever. This is the quiet end, the slow fade, the universe growing cold and dark and still. It is not an end in fire, not an end in violence, just an end in silence. And it will take a very, very long time. But it is also possible that something else will happen. That dark energy will change. That new physics will intervene. Perhaps the universe will collapse. Perhaps it will rip apart. Perhaps it will cycle, ending and beginning again. We do not know. The future is uncertain. The universe keeps its secrets. But for now, the stars are still burning. The galaxies are still turning. And we are here in this brief moment to witness it. That is a gift, a quiet gift, a moment of light in the vast darkness of time. And we can rest in that. We can let go. We can simply be here, now, without needing to know what comes next. The universe will continue. It will unfold. It will do what it does. And we can rest. There is a type of star that barely shines. It is called a brown dwarf. And it is not quite a star, not quite a planet. It is something in between. Brown dwarfs form the same way stars do, from collapsing clouds of gas and dust, but they do not have enough mass to ignite hydrogen fusion in their cores. They are too small, too light. The pressure and temperature at their center never reach the point where hydrogen atoms can fuse into helium. And so, they do not shine the way stars do. They do not burn steadily for billions of years. Instead, they glow faintly with leftover heat from their formation. They slowly cool. They fade. Brown dwarfs are dim, very dim, difficult to detect. They emit most of their light in the infrared, invisible to our eyes. But they are out there, scattered throughout the galaxy, silent, cooling, almost invisible. Some brown dwarfs are alone, drifting through space, never part of a solar system, never orbiting a star. Others are companions, orbiting larger stars, or orbiting each other in binary pairs. They are the failed stars, the objects that almost made it, but did not quite have enough mass. And yet, they are fascinating, because they blur the line between stars and planets. They show us that the universe does not have sharp categories, that there is a continuum, a spectrum of objects, each slightly different from the next. Brown dwarfs are also important for understanding how stars form, how planets form, how solar systems come together. They are part of the population, part of the inventory of objects in the galaxy, and they remind us that not everything in the universe is bright, not everything shines. Some things are dim, quiet, almost invisible, but they are still there, still real, still part of the story. Another dim object in the universe is a white dwarf. A white dwarf is the remnant of a star like the Sun. After the star has exhausted its fuel, after it has shed its outer layers, what remains is the core. The core is incredibly dense. A white dwarf with the mass of the Sun is only about the size of the Earth. All that mass compressed into such a small volume. The density is staggering. A teaspoon of white dwarf material would weigh several tons. White dwarfs do not burn. They do not produce energy through fusion. They simply glow with leftover heat. Heat that was trapped in the core during the star's lifetime. And they cool, very slowly. A white dwarf starts out hot, tens of thousands of degrees. It shines with a bright white light, but over time, it cools. It fades. It shifts from white to yellow to red. And eventually, after trillions of years, it will cool completely. It will become a black dwarf, a cold, dark, dead star. No black dwarfs exist yet. The universe is not old enough. Even the oldest white dwarfs are still faintly glowing, but in the far future, they will exist. The final remnants of stars, cold and dark and silent. White dwarfs are stable. They are held up by something called electron degeneracy pressure, the pressure that comes from the quantum behavior of electrons. Electrons cannot occupy the same space. They resist being compressed, and this resistance is what keeps a white dwarf from collapsing further. But there is a limit. If a white dwarf gains too much mass, if it exceeds about 1.4 times the mass of the Sun, the electron degeneracy pressure is not enough. The star collapses, and it explodes. This explosion is called a Type 1, a supernova, and it is one of the brightest events in the universe. Type Ia supernovae are important for cosmology because they are so bright and so consistent. They can be seen across vast distances, and they can be used as distance markers, as standard candles to measure the expansion of the universe. It was by studying type Ia supernovae that scientists discovered dark energy, that the expansion of the universe is accelerating. But before the explosion, before the supernova, there is just a white dwarf, cooling quietly, fading slowly, waiting. And most white dwarfs will never explode. Most will simply cool and fade and become black dwarfs billions of years from now. They are the quiet endings, the peaceful deaths of ordinary stars. And they remind us that not all endings are violent, that most things fade gently, that silence is more common than noise. There is another type of stellar remnant, more extreme than a white dwarf, more dense, more strange. A neutron star. Neutron stars form when very massive stars explode as supernovae. The core collapses, and if it is heavy enough, it does not stop at the white dwarf stage. It collapses further. The protons and electrons in the core are squeezed together so tightly that they combine. They become neutrons, and the entire core becomes a ball of neutrons. A neutron star is incredibly dense, far denser than a white dwarf. A neutron star with the mass of the Sun is only about 20 kilometers across, about the size of a city, and a teaspoon of neutron star material would weigh as much as a mountain. The surface of a neutron star is smooth, hard, made of atomic nuclei packed so tightly that they form a solid crust. Beneath the crust, the matter is even more exotic. A superfluid of neutrons, a sea of particles that flows without friction, without resistance. And at the very center, the core, the conditions are so extreme that we do not know what happens. The matter may break down into quarks. It may form something entirely new, something we have no name for. Neutron stars are also incredibly strong. The magnetic field of a neutron star is trillions of times stronger than Earth's magnetic field. Some neutron stars spin very fast, hundreds of times per second. They are called pulsars. Pulsars emit beams of radiation from their magnetic poles, and as the star spins, those beams sweep across space like a lighthouse beam. If the beam sweeps past Earth, we detect a pulse, a brief flash of radio waves or X-rays, and we see the star blinking on and off very rapidly, very precisely. Pulsars are some of the most accurate clocks in the universe. Their pulses are so regular, so consistent, that they can be used to test the laws of physics, to detect gravitational waves, to measure the expansion of space. But not all neutron stars are pulsars. Some spin more slowly. Some have weaker magnetic fields. Some do not emit beams that point toward Earth. Those neutron stars are silent, invisible. We only know they are there if they are part of a binary system, if they are pulling gas from a companion star. Neutron stars are the densest objects in the universe. Aside from black holes, they are the edge of matter, the limit of how compressed ordinary matter can be. Beyond that limit, there is only one possibility: a black hole. And black holes are where the quiet mysteries become even deeper. There is a mystery about what happens inside a black hole. We know what happens at the event horizon. We know how time behaves, how light behaves, how gravity pulls. But inside, beyond that boundary, we can only speculate. General relativity tells us that at the center of a black hole is a singularity, a point of infinite density, a place where space and time break down, where the equations stop working. But we do not know if singularities truly exist. Perhaps something else happens. Perhaps quantum mechanics prevents the collapse from reaching infinite density. Perhaps the matter bounces back. Perhaps it tunnels to another universe. These are speculations, possibilities, but we have no way to test them, because nothing can escape from inside a black hole. No information, no signal, no light. Whatever happens inside remains hidden, forever sealed behind the event horizon. This is called cosmic censorship. The idea that singularities are always hidden, that the universe does not allow us to see them directly. It is as if the universe has a modesty, a reluctance to reveal its most extreme states, its most violent breakdowns. And perhaps that is for the best. Perhaps there are some things we are not meant to see, some places where the laws we know simply do not apply. Black holes are boundaries, edges, places where our understanding ends and mystery begins, and they are comfortable with that. They do not demand to be understood. They simply exist, quiet, patient, keeping their secrets. Another mystery involves the rotation of black holes. Black holes can spin, and when they spin, they drag space-time around with them. This is called frame dragging. The spinning black hole twists the fabric of space and time, pulling everything nearby into a rotating motion. Near a spinning black hole, it becomes impossible to stand still. Space itself is rotating, and anything in that space is carried along with it. This creates a region called the ergosphere, a zone outside the event horizon where nothing can remain stationary, where everything must move in the direction of the black hole's rotation. But the ergosphere is not inside the event horizon. It is possible to enter the ergosphere and escape. It is possible to extract energy from it. This is called the Penrose process, and it is one of the most remarkable features of spinning black holes. By dropping an object into the ergosphere and carefully timing its trajectory, it is possible to extract rotational energy from the black hole. The object can split into two pieces. One falls in. The other escapes, carrying away more energy than it started with. The black hole loses a tiny amount of its spin, and the escaping object gains energy. This is a theoretical process. It has never been observed, but it is allowed by the laws of physics. It is possible. And in the far future, if intelligent beings still exist, if they need energy and the universe is cold and dark, they might use this process. They might harvest energy from spinning black holes, because black holes will be the last sources of energy, the last warm places in a frozen universe. But that is a very long time from now, trillions upon trillions of years. For now, black holes are simply there, spinning quietly, warping space-time, waiting. There is also a mystery about where black holes come from in the first place. We know that stellar mass black holes form from supernovae, from the collapse of massive stars. But what about the supermassive black holes at the centers of galaxies? These black holes are enormous, millions or billions of times the mass of the Sun, and they formed very early in the history of the universe. We see supermassive black holes in galaxies that are less than 1 billion years old, galaxies that formed shortly after the Big Bang, and we do not know how they grew so large so quickly. It takes time for a black hole to grow. It must consume matter, pull in gas and stars, merge with other black holes. But there does not seem to have been enough time for these supermassive black holes to reach their size through normal processes. So how did they form? One possibility is that they started large, that they formed from the direct collapse of massive clouds of gas in the early universe. Another possibility is that they formed from the collapse of the first stars, stars that were much more massive than any star today, stars that lived fast and died young, leaving behind large black holes. Or perhaps they grew through repeated mergers. Perhaps many smaller black holes came together again and again, building up mass quickly. We do not know. The observations are still unclear. The theories are still being tested. But it is one more mystery, one more question about the history of the universe. And it reminds us that even the largest, most powerful objects in the cosmos have origins we do not fully understand. Supermassive black holes are also surprisingly influential. At the center of almost every large galaxy, there is a supermassive black hole, including our own. The Milky Way has a black hole called Sagittarius A star. It has a mass of about 4 million suns, and it sits at the very center of the galaxy, quiet, mostly dormant, occasionally consuming a small amount of gas or a stray star. But in other galaxies, the central black hole is more active. It pulls in large amounts of matter. Gas spirals inward, heating up, glowing brightly. Jets of particles shoot outward at nearly the speed of light. These active black holes are called quasars, or active galactic nuclei. They are among the brightest objects in the universe. A single quasar can outshine an entire galaxy of stars, and yet the light does not come from the black hole itself. It comes from the matter falling into the black hole. The accretion disk, the swirling, glowing ring of gas just outside the event horizon. As the gas spirals inward, it heats up. Friction converts gravitational potential energy into heat. The temperature rises. The gas glows. And just before it crosses the event horizon, just before it disappears forever, the gas emits a final burst of light, a last farewell. That light travels outward, across space, across billions of light years, and it reaches us. Quasars are so bright that we can see them at the edge of the observable universe. They are beacons, markers of the early cosmos, signs of black holes that were already supermassive when the universe was young. But they are also temporary. Quasars do not last forever. As the black hole consumes the nearby gas, the supply runs out. The accretion disk fades. The jets shut off. The quasar becomes quiet. And the galaxy settles into a quieter state. The black hole remains, but it is no longer feeding, no longer glowing. It becomes dormant, like Sagittarius, a star, like the black holes at the centers of most galaxies today. They are sleeping giants, waiting, ready to wake if new gas arrives. But for now, still, there is a connection between black holes and the galaxies around them. When astronomers measure the mass of a supermassive black hole and compare it to the properties of its host galaxy, they find a correlation. The more massive the black hole, the more massive the central bulge of the galaxy. The two are linked. This is surprising, because the black hole is tiny compared to the galaxy. The event horizon of a supermassive black hole is only a few light hours across. The galaxy is hundreds of thousands of light years across. And yet, they seem to know about each other. They seem to have co-evolved. This suggests that black holes play a role in shaping galaxies, that their activity, their jets, their radiation affects the gas and stars around them. When a quasar is active, its jets can blow gas out of the galaxy. They can heat the gas, preventing it from collapsing and forming new stars. This is called feedback. The black hole regulates the growth of the galaxy. It prevents the galaxy from forming too many stars too quickly. And this feedback may explain the correlation. The black hole and the galaxy grow together. They influence each other. They reach a balance. When the black hole is too small, it does not provide enough feedback. The galaxy forms stars quickly. The black hole grows. When the black hole is too large, it provides too much feedback. Star formation slows, the galaxy stops growing, and eventually they settle into a stable state, a balance, a quiet equilibrium. This is one of the surprising discoveries of modern astronomy, that black holes, the darkest objects in the universe, play a bright role in the evolution of galaxies, that destruction and creation are linked, that endings and beginnings are part of the same process. There is a type of galaxy that is shaped by black holes, an elliptical galaxy. Elliptical galaxies are smooth, round. They do not have spiral arms. They do not have much gas or dust. They are made mostly of old stars, and they are common. About a third of all large galaxies are elliptical. Elliptical galaxies form through mergers. When two spiral galaxies collide, they mix. Their stars pass through each other. Their gas clouds collide and form new stars. And over time, the two galaxies merge. They become one, and the result is an elliptical galaxy. During the merger, gas falls toward the center. It feeds the supermassive black holes. The black holes grow, they become active. They emit jets and radiation, and that activity blows out the remaining gas, the gas that would have formed new stars. So the elliptical galaxy ends up with very little gas, very few young stars, just old stars orbiting in random directions. The galaxy is quiet, settled, red, and at its center, a supermassive black hole, dormant, having consumed its meal, having shut off the star formation, having shaped the galaxy into its final form. Elliptical galaxies are the end state, the retirement, the quiet phase. They are what galaxies become after a lifetime of activity, after mergers and star formation and black hole growth. They are peaceful, stable, slowly fading, and they will remain that way for a very long time. There is a question about whether we live in a typical place in the universe. Our solar system is in the outskirts of the Milky Way, about halfway out from the center, in a quiet region, away from the dense clusters of stars near the core. This is a good place to be, quiet, stable, safe. Near the center of the galaxy, stars are packed closely together. Gravitational interactions are common. Stellar encounters could disrupt planetary systems. Supernovae are more frequent. It is a more dangerous place, more chaotic. Out here, in the suburbs of the galaxy, things are calmer. The stars are farther apart. Disturbances are rare. And that may be important for life, for planets like Earth, for stable conditions over billions of years. If we were closer to the center, Earth might not have had the long, stable history that allowed life to evolve. So in some sense, we live in a special place, a Goldilocks zone, not too close to the center, not too far out in the empty regions, just right. But this raises a question. Is this typical? Do most life-bearing planets form in places like this? Or are we unusually lucky? We do not know. We do not yet know how common life is in the universe. We do not know how sensitive it is to location. But it is something to think about, something to wonder. That perhaps our place in the universe is not random. That perhaps the conditions here are part of why we exist. That location matters. That structure matters. That the universe has regions more favorable to life, and we happen to be in one of them. And that is another quiet mystery. another piece of the puzzle. There is also a mystery about the shape of the Milky Way itself. The Milky Way is a spiral galaxy. It has a central bulge, a disk, spiral arms, a halo of old stars. But the disk is not flat. It is warped, twisted. At the edges, far from the center, the disk curves upward on one side and downward on the other. This warp is subtle, but it is there, and we do not fully know why. One possibility is that the warp is caused by the gravity of nearby galaxies. The Magellanic Clouds, two small galaxies that orbit the Milky Way, may be pulling on the disk, distorting it. Another possibility is that the warp is a leftover from a past collision, a merger with a smaller galaxy long ago that left the disk slightly bent. Or perhaps the warp is simply a natural feature, something that happens to spiral galaxies over time as they rotate and evolve. We do not know. The observations are difficult. The disk is large, and we are inside it, which makes it hard to see its overall shape. But the warp is there, a gentle curve, a twist, and it reminds us that even familiar objects we see every night, can hold surprises. The Milky Way is our home galaxy, but we are still learning about it, still discovering its structure, still mapping its shape. And there are still mysteries, still questions. Another mystery involves the halo of the Milky Way. The halo is a spherical region surrounding the disk. It is made of old stars, globular clusters, and dark matter. The stars in the halo are ancient, some of the oldest stars in the universe. They formed more than 13 billion years ago, shortly after the Big Bang, and they are moving in random directions, not rotating with the disk, not following the spiral structure, just orbiting the center of the galaxy in elliptical paths. These stars are remnants, survivors. They are what remains of the early universe, the first generation of stars, and they tell us about the history of the Milky Way, about how it formed, about what it was like when it was young. By studying the halo stars, astronomers can reconstruct the past. They can see traces of ancient mergers, events that happened billions of years ago, smaller galaxies that were consumed by the Milky Way, leaving behind streams of stars in the halo. The halo is a fossil record, a history book, a record of everything the Milky Way has experienced, and it is still being written. Even now, the Milky Way is consuming smaller galaxies. The Magellanic Clouds will eventually be absorbed. Their stars will join the halo. This is a slow process, a quiet process, a gradual accumulation, and it is how large galaxies grow, by consuming smaller ones, by merging, by gathering mass over time. The universe is not static. It is not frozen. It is evolving, changing, slowly rearranging itself. And we are part of that process, part of the flow, part of the ongoing story. There is a question about whether the Milky Way will always look the way it does now. The answer is no. Galaxies change, they evolve, and the Milky Way is no exception. In about 4 billion years, the Milky Way will collide with Andromeda. This collision is inevitable. The two galaxies are moving toward each other, pulled together by gravity. And when they meet, they will not simply bounce off. They will pass through each other. Their stars will intermingle. Their gas clouds will collide. And over the course of several passes, several 100 million years, they will merge. They will become one galaxy. This new galaxy has already been given a name, Milkomeda, or sometimes Milk-Dromeda. It will be an elliptical galaxy, larger than either the Milky Way or Andromeda, red, smooth, filled with old stars, and the Sun, if it still exists, will be part of it, orbiting in some new path, in some new region. But this is nothing to fear. The collision will not harm the solar system. Stars are so far apart that the chance of any collision is almost zero. The Sun will simply find itself in a new galaxy, with a new sky, new constellations, new neighbors, and life on Earth, if it still exists, will look up and see a different universe, a different arrangement of stars. But that is billions of years away. For now, the Milky Way is stable. Andromeda is still far away, and the collision is a distant future. There is time, so much time, and in that time the universe will continue, slowly, quietly, unfolding. There is a mystery about the very edge of the universe, the observable universe. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It is about 93 billion light-years across, and it is expanding. Every moment, more of the universe comes into view. More light arrives from distant regions. But there is a limit, a horizon. Beyond that horizon, light has not yet had time to reach us, and we will never see it, because the universe is expanding, and the more distant regions are moving away from us faster than light can travel through space. So there is a boundary, a cosmic horizon, and beyond it, the universe continues. But we cannot see it, cannot know what is there. This is humbling. It means that the universe we observe is only a small part of the total universe. The full universe may be vastly larger, perhaps infinite, and we will never know. We can only see our small patch, our observable bubble. But that bubble is still enormous. It contains hundreds of billions of galaxies, trillions of stars, more planets than we can count. And within that bubble, there is so much to explore, so much to discover, so many mysteries. We do not need to see the whole universe to be amazed by it, to be humbled by it, to find peace in it. The part we can see is enough, more than enough, and it is ours to wonder about, to study, to rest in. There is a type of light we cannot see with our eyes, infrared light. It is all around us, emitted by warm objects, by stars, by planets, by our own bodies. Everything that has heat emits infrared radiation. It is invisible to us, but it is there. A constant glow, a thermal signature. In space, infrared light is important because it can pass through dust. Visible light is blocked by dust clouds, scattered, absorbed. When we look at certain regions of space with optical telescopes, we see darkness, opacity, walls of dust. But when we look with infrared telescopes, we can see through. We can peer into the hearts of dust clouds, into star-forming regions, into the centers of galaxies. Infrared light reveals what is hidden. It shows us the stars being born, the planets forming, the warm gas swirling in the depths of molecular clouds, and it shows us the cool objects, the objects too dim to see in visible light. Brown dwarfs, cold planets, distant galaxies shrouded in dust. The universe looks different in infrared, warmer, fuller, more textured, and it reminds us that what we see is only part of what is there, that light comes in many forms, that our eyes show us just one slice of reality. There are other forms of light, other wavelengths, radio waves, microwaves, ultraviolet, X-rays, gamma rays. Each one reveals something different. Each one shows us a different aspect of the universe. Radio telescopes see cold gas, the clouds between the stars, the hydrogen that fills the galaxy, the faint signals from pulsars and distant galaxies. X-ray telescopes see hot gas, the million-degree plasmas in galaxy clusters, the material falling into black holes, the remnants of supernovae. Gamma-ray telescopes see the most energetic events, the explosions, the collisions, the places where particles are accelerated to nearly the speed of light. Together, these different forms of light give us a complete picture, a full view of the universe. Not just what shines, but what glows faintly, what radiates, what exists in the darkness. And that picture is richer than we ever imagined, more complex, more layered. The universe is not just made of things we can see, it is made of things we can detect, things we can infer, things we can measure. And each measurement reveals more. Each observation adds to the story. There is a mystery about the very first light. The cosmic microwave background is the oldest light we can see, but it is not the first light that was ever emitted. Before the cosmic microwave background, the universe was opaque. Light could not travel freely. It was scattered immediately, trapped in the dense fog of particles. But there was light. Light from the Big Bang itself. Light from the earliest moments. That light still exists, but it has been redshifted, stretched by the expansion of the universe, shifted to longer and longer wavelengths. By now, that earliest light has been stretched into wavelengths we cannot detect, longer than radio waves, longer than anything our instruments can measure. It is still there, filling the universe, a ghost of the beginning, but invisible, beyond our reach, and perhaps it always will be. Perhaps there are limits to how far back we can see, how far back we can probe. The cosmic microwave background is a wall, a boundary in time, the earliest moment we can observe directly. Before that, the universe is hidden, veiled, opaque, and we can only infer what happened, only model, only calculate. We cannot see it, cannot photograph it, cannot witness it. It is a mystery that may remain forever, a question we may never fully answer. But that is part of the beauty of science, part of the humility it teaches us. There are limits to what we can know, boundaries to our understanding, and that is okay. We do not need to know everything. We do not need to see everything. We can rest in the knowledge we have and be at peace with the mysteries that remain. There is another mystery about the nature of space itself. Is space continuous, or is it discrete? At the largest scales, space appears smooth, continuous. You can move through it in any direction. You can divide it into smaller and smaller regions, infinitely. But some theories suggest that space is not truly continuous, that at the smallest scales, space is made of discrete units, tiny chunks, pixels of reality. This is an idea from quantum gravity, the attempt to unite quantum mechanics and general relativity. In quantum mechanics, energy comes in discrete units, quanta. Photons are quanta of light. Electrons are quanta of electric charge. Perhaps space itself is also quantized. Perhaps there is a smallest possible length, a fundamental unit below which space cannot be divided further. This length is called the Planck length. It is incredibly small, about 10 to the minus 35 meters, far smaller than an atom, far smaller than anything we can measure. If space is quantized, if it is made of Planck-sized units, then the universe is fundamentally grainy, pixelated, like a digital photograph when you zoom in too far. But we do not know if this is true. We have no way to test it. The scales are too small. The energies required to probe those scales are far beyond anything we can produce. It is a theoretical idea, a possibility, a hint of what might lie at the very foundation of reality. And it is another reminder that the universe may be stranger than we can imagine, that the fabric of space and time may have a structure we cannot see, a hidden architecture. Or perhaps space is truly continuous. Perhaps there is no smallest length. Perhaps you can divide forever. We do not know. The mystery remains. But it is a quiet mystery, a gentle puzzle, not something we need to solve tonight, just something to wonder about, something to drift through as we rest. There is a phenomenon that connects the very small and the very large: quantum fluctuations. At the quantum level, empty space is not truly empty. It is filled with fluctuations, tiny bursts of energy, virtual particles that appear and disappear in an instant. These fluctuations are random, unpredictable. They arise from the uncertainty principle, the idea that at the quantum level, nothing is perfectly still. Nothing is perfectly certain. And these tiny fluctuations, these random variations, are what seeded the structure of the universe. During inflation, when the universe was expanding faster than light, quantum fluctuations were stretched, amplified, frozen into the fabric of space. Those frozen fluctuations became the tiny variations in density that we see in the cosmic microwave background. And those variations, over time, grew. They attracted matter. They formed the seeds of galaxies, the seeds of stars, the seeds of everything we see. So the structure of the universe, the pattern of galaxies and voids, the cosmic web itself, all of it arose from quantum fluctuations, from randomness at the smallest scale. This is one of the most profound connections in physics, the link between the quantum world and the cosmic scale. It shows us that the smallest things matter, that tiny fluctuations can have enormous consequences, that randomness and order are intertwined, and it is beautiful, elegant, a deep truth about how the universe works. From uncertainty comes structure. From chaos comes form. From the random dance of quantum fields comes the majestic architecture of galaxies. It is a reminder that the universe is whole, that everything is connected, that there are no separate realms, only different scales of the same reality. And we can rest in that. We can let go of the need to separate things, to categorize, to divide. The universe is one thing, and we are part of it. There is a question about whether the laws of physics are the same everywhere. We assume they are. We assume that the speed of light is the same in distant galaxies, that gravity works the same way, that atoms behave the same way, and all the evidence supports this. When we observe distant galaxies, we see the same physical processes, the same spectral lines, the same behavior. But we cannot be certain. We can only observe a small part of the universe, the observable universe, our cosmic bubble. Beyond that, we do not know. Perhaps the laws are different. Perhaps the constants have different values. Perhaps physics works in a completely different way. This is speculation, but it is allowed, because we cannot check. And if the multiverse exists, if there are many universes with different properties, then the laws almost certainly vary. Each universe would have its own physics, its own constants, its own rules. We would live in just one of them, the one where the laws allow us to exist. But we would never know about the others. We would never see them, never interact with them. They would be forever separate, forever beyond our reach. This is a strange idea, a disorienting idea, but also a humbling one. It suggests that our universe, the one we know, the one we study, is not special, not unique, just one among many. And the laws we discover, the constants we measure, are not fundamental truths about reality. They are just the local rules, the conditions of our particular universe. This changes the meaning of a law of nature. It makes it contingent, dependent, specific to our corner of existence. And it raises questions we may never answer, questions about why our laws are what they are, why our universe is the way it is. But again, these are questions we can hold lightly. We do not need to solve them. We can simply let them be. The universe we live in is enough. The laws we have discovered are enough. The mysteries we can explore are enough. And we can rest in that. There is a type of star that pulses, a variable star. Variable stars change in brightness. They dim and brighten over and over in regular cycles. Some variable stars pulse because they are unstable. They expand and contract. Their outer layers move in and out like a slow heartbeat. As the star expands, it cools and dims. As it contracts, it heats and brightens. This cycle can take days, or weeks, or months, and it is remarkably regular, predictable, a cosmic clock. One type of variable star is especially important: Cepheid variables. Cepheids are large, bright stars, and their pulsation period is directly related to their intrinsic brightness. The longer the period, the brighter the star. This relationship makes Cepheids useful as distance markers. If you observe a Cepheid and measure its period, you know how bright it truly is. And if you know how bright it truly is, and you measure how bright it appears, you can calculate how far away it is. This is how Edwin Hubble measured the distances to other galaxies. He found Cepheids in Andromeda. He measured their periods. He calculated their distances, and he discovered that Andromeda was far away, so far that it could not be part of the Milky Way. It had to be a separate galaxy. This was a revolutionary discovery. It showed that the universe was much larger than anyone had thought, that the Milky Way was just one galaxy among many, and it opened the door to modern cosmology, to the study of the universe as a whole. Cepheids are still used today. They are one of the first steps on the cosmic distance ladder, the series of methods we use to measure distances to farther and farther objects. And they are reliable, steady, pulsing quietly in the darkness, telling us how far away they are. There are other variable stars that vary for different reasons, eclipsing binaries, two stars orbiting each other. When one passes in front of the other, the combined light dims. When they are side by side, the light is brighter. Flare stars, small stars that occasionally brighten suddenly, emitting bursts of energy. Novae, white dwarfs that accumulate matter from a companion star and occasionally explode, brightening dramatically before fading again. Each type of variable tells us something. Each one reveals a different aspect of stellar physics, and together they remind us that stars are not static. They are dynamic, changing, evolving. The night sky may appear still, unchanging, but if you watch carefully, if you measure precisely, you see that it is alive, that stars breathe, pulse, flare, that the universe is always in motion, always transforming. And we can watch, we can observe, we can rest in the knowledge that even the stars are restful in their changes, that their cycles are slow, predictable, gentle. There is a mystery about the fate of planets. There is a place where all the mysteries converge. In your mind, in your awareness, in this moment. All the questions we have explored, all the puzzles, all the unknowns, they exist because we are here to ask them, to wonder about them. The universe existed for billions of years, before conscious beings, before observers, before anyone to notice the stars, the galaxies, the slow unfolding of space and time. And it will exist for billions more, after we are gone, after consciousness has faded, after the last observer has disappeared. But right now, in this brief moment, the universe is aware of itself, through us, through you. You are made of atoms, forged in stars, scattered through space, gathered by gravity, assembled into planets, into oceans, into cells, into thoughts. You are stardust, contemplating stars, the universe, looking at itself, asking questions, seeking understanding. This is extraordinary, rare, perhaps unique in all the cosmos, or perhaps common. We do not know, but either way, it is precious. This moment, this awareness, this quiet wondering, and it does not require effort, does not require struggle, does not require staying awake. The universe will continue, with or without your attention, your consciousness, your awareness. It has no need of witnesses, of observers, of understanding. It simply is, and you can simply be part of it, resting in it, held by it. There is a rhythm to everything. The expansion of the universe, the rotation of galaxies, the orbits of stars, the cycles of planets, day and night, seasons, tides, life and death, waking and sleeping, all of it, part of the same rhythm, the same flow, the same dance, and you are dancing, even now, even as you rest. Your heart beats, your lungs breathe, your cells divide and repair, your brain processes, sorts, consolidates, all without your direction, all without your effort. The body knows what to do, the universe knows what to do, and you can trust that knowing, can surrender to that rhythm. There is nothing to control, nothing to force, nothing to make happen, just the natural unfolding of rest, of restoration, of sleep, like the slow cooling of a white dwarf, like the gentle drift of galaxies through space. Everything happens in its own time, at its own pace, and sleep will come when it comes, not before, not after, just when it is ready. There is a concept in astronomy called deep time, the vast spans of cosmic history, billions of years, timescales so long that human experience disappears into them like a grain of sand on an infinite beach. But deep time also reminds us that this moment, this brief flicker, this instant of consciousness is no less real, no less valid, for being temporary. A mayfly lives for one day, but that day is its entire life, its whole existence, complete, whole, perfect, and we live for decades, perhaps a century, a brief moment in cosmic time, but our moment is complete, whole, perfect. This night, this rest, this sleep is part of that, part of your moment, part of your experience, and it deserves your gentleness, your acceptance, your peace. You do not need to achieve anything tonight, not even sleep, just rest, just stillness, just being here. And if sleep comes, it comes, and if it does not, that is also okay. The body will rest, regardless, will restore itself in its own way. There is a mystery about gratitude. Why do we feel grateful for existence, for beauty, for the universe? Gratitude serves no evolutionary purpose, provides no survival advantage, and yet we feel it, perhaps. Gratitude is the universe appreciating itself through us, a moment of recognition, of acknowledgement that all of this vast complexity, this elegant structure, this beautiful mystery exists, and we are here to witness it for however brief a time. That is worth gratitude, worth wonder, worth peace. The stars do not know they are beautiful. The galaxies do not know they are vast. The universe does not know it exists, but you do. You know, you see, you understand, even if only partially, imperfectly. And that knowing, that seeing, is a gift, not to you, but through you, to the cosmos. You are how the universe knows itself. And tonight, you can rest in that knowing, can let it settle into your bones, your breath, your stillness. There is nothing more to do, nowhere else to be, no other question to answer, just this, just now, just rest. The mysteries will remain, the stars will continue burning, the galaxies will continue turning, the universe will continue expanding, all of it happening slowly, quietly, patiently. And you are part of that patience, part of that quiet, part of that slow unfolding. Your breathing is slowing now. Your thoughts are spacing out. Your body is settling deeper. This is natural. This is right. This is how it should be. The weight of everything is lifting. The questions are fading. The need to know, to understand, to stay awake is dissolving like morning mist in sunlight, like stars fading at dawn, like consciousness slipping into sleep. And you can let it slip, can allow it to fade, can surrender to the darkness, to the quiet, to the rest. There is no effort required, no technique to master, no goal to achieve, just letting go, just releasing, just being. The universe is here, has always been here, will always be here, and you are safe in it, held by it, part of it. The cosmic web stretches across billions of light years, connecting everything to everything else, and you are one of those connections, one thread in the web, woven into the fabric of reality. You cannot fall out of the universe, cannot be separate from it. You are it, and it is you, and in that unity, that oneness, there is deep peace, deep rest, deep letting go. The boundaries between you and the universe are dissolving now. The separation between waking and sleeping is blurring. You are floating, drifting, becoming less solid, less defined, less individual, just awareness, fading into the whole, into the darkness, into the cosmic night. And that is perfect, that is natural, that is exactly how it should be. Sleep is not an absence, it is a presence, a state of being, as real, as valid as waking, just different, just quieter, just deeper, and you are moving into it now, gently, naturally, without resistance. The stars are there in the darkness, even when you cannot see them Even when your eyes are closed, the universe is there, unfolding, expanding, existing, and you are there too, resting in it, part of it, one with it. There is nothing left to say. The mysteries are quiet now. The questions have faded. The universe continues its slow dance, and you can sleep now, deeply, peacefully, completely. Rest, sleep, be here in the quiet, in the dark, in the infinite peace of the cosmos. Sleep now, sleep.